Well, welcome back, SCC students, chemistry students. Hope you had a good week. We're getting down to the wire as far as the end of the semester. I'm looking at the schedule. Obviously, today is the 16th. What my plan today is to finish up chapter 12. We are on slide 8 of chapter 12. This won't have much more to finish on that. And then finish up 13 today. That is a short chapter also. And then whatever time we got left, I'm here for open for questions. If you don't have any, we'll call it a day. All right. Now, next Friday, we'll do basically now we're going to probably be doing every Friday now a chapter. And so we got chapter 14. We'll knock that out next Friday. Again, you have the advantage here that we can use the rest of the time for as an office hour / question and answer session after we're done with the chapter. Okay. And if you don't have anything, well, okay, have a good afternoon and see you the following Friday. So the following Friday, which would be the 30th, I plan on chapter 15. And then finally, on the 7th of May, that would be chapter 16, which is the gases. Again, those 14, 15, and 16 are relatively small or short chapters. And then for the 14th, we'll make that an official, what I call a study day. Obviously, we're done with the chapters by the 7th. So the 14th, you have exam number 5, the last one, I believe. And we'll leave that open up for, again, questions and answers. If you have any, I'll be here. And if you're not, well, have a good weekend because the following Friday is the final. Okay. Now, if there's a problem with that particular day, because what happens with the Friday class with SCC, and I've asked them to address this, they make the final week classes, exams only Monday through Thursday. And I'm like, well, guys, I got a Friday class. You should extend that to Friday because that's what they signed up for Friday. And so officially, we're out of the finals week because it ends on Thursday. But I've always kept it on Friday because you guys, this is your time. This is what you signed up for. And as far as I'm concerned, it's your final day. But having said that, I need to, as soon as you're done, go through all my grading, make sure everything's done, and then post them the following day, the next day by Saturday. So if there's a problem with respect to taking the final on the 22nd, the only latitude I had is to have you take it beforehand. Okay. So keep that in mind. I can't give it to you afterwards because I have to get my grades. Yeah. If you already contacted me and made arrangements to have a final, that's perfect. Remind me again during that time period that this is the day you need it. And I'll make sure that happens. Okay. Not a problem taking it early if you have to. There's a lot of debate with respect to taking the extra week. I opted to take the extra week for not only you guys, but my guys at SCC, at GCC. Given we have that 2 weeks off and then all the problems with, the COVID thing as we've been fighting with for a year now, and then the whole system being shut down and trying to put it back online. I knew there were going to be some problems with email and Canvas. I'm still having challenges with Canvas occasionally. And, and then Cox is having their little trouble. So if FYI, if I go away, it's because Cox is doing something. I don't know what the heck's going on. It did that to me yesterday a couple of times, day before too, in the evening. So if I go away, hang loose, I'll reboot, wait for Cox to come back on. If I'm not back on in 15 minutes and Cox has shut down the whole area and I can't get back on, I'll try to shoot an email through my phone and get it to you guys. And we just call it a day and make up time next time we meet. Okay? Just FYI. So that's the plan. Today, 12 to 13. The 23rd, following next Friday, chapter 14, the 30th, chapter 15, the 7th of May, chapter 16, and then the following Friday, the 14th, it starts a study day, and that's literally our last day that we would meet Zoom-wise. And then the final will be available for you that following Friday to take. I can't leave it open for the weekend, but I will open it up. I might try and debate. I might open it up. In fact, that's what I'll do. I open it up for the full week, but Friday is the due date. Yeah, let me make a note of that for that finals week. And if you have to do the week before, obviously you've emailed me, but send me in a remind email a day or so before you gotta take it earlier so I can make sure it's set up. Okay, week available. All right, any questions about that? No? Okay, well, let us jump into chapter 12 then and continue where we landed up. And we stopped in chapter slide 8, according to my notes, and I'm backing it up just to kind of refresh your memory. Here, what we're doing is we're going to calculate the molar mass of a compound, okay? So to calculate the molar mass of any compound, we obviously have to add up the atomic weights of every atom in that compound and how many atoms they are of that compound. Okay, but before we do that, we got to write a formula. So this is where it comes in, where you see the name and you got to convert that name to a formula. And we went through this scenario. I'll go through it very quickly again. Okay, so we have here the name, geez, over here, barium hydroxide, okay? Barium hydroxide. Well, obviously we're working with an ionic compound, okay? We got a metal and a non-metal polyatomic ion, hydroxide. If you go to the polyatomic ion table, you'll see that hydroxide has that formula here, OH, that's the base. Remember that chapter about the base, something that produces a hydroxyl group, okay? And barium, we got to put that in ionic form. That allows us to make sure that we put it together in the right number of cations and anions. So we know that barium, find that in the periodic table, it is in group 2A, which tells you it has 2 valence electrons. Therefore, when it becomes ionic, it has structure the oxidation state of a +2 charge because it's a metal. It will lose those 2 valence electrons. Okay. Now we got to put them together. The hydroxides have a -1. That tells me I need 2 hydroxides to counter the +2 of the barium ion. With the 2 here, that also tells me that I need parentheses around the hydroxide. Because remember, if we need more than one of the polyatomic ions, we use a parentheses and then the subscript to tell us how many we have. And so our formula becomes Ba parentheses OH and parentheses subscript Q. Okay. So with that being said, that tells us we have one barium, not 2 barium, 1 barium, okay, 2 oxygens, and 2 hydrogens, okay, 2 hydrogens. So the barium has a atomic weight of 137.33. I obtained that from the periodic table we supply. Do use those atomic weights, okay? The oxygens each have 16, so that's 32.00 grams per mole. And then the hydrogens each have a atomic weight of 1.01. There's 2 of them. So we end up with 2.02. Okay. Add that number up. Remember, the units for the atomic weights are grams per mole, grams per mole. And remember this, that's a ratio, grams over moles, a ratio that you can write either as moles over grams or grams over moles. Okay, so with that being done, let me clear up my mess here. And we wrote the formula. Then we add up the total mass, and we end up with an atomic or molar mass, okay, of 171.35 grams per mole. Now, when we talk about the elements themselves, we use the term atomic weights. That's what it is. It's the atomic weights of the one atom, whatever element, whatever that element will be. But when the elements come together to make compounds, then the cumulative atomic weights, we refer it as the molar mass. Okay, so molar mass talks about a compound that you're trying to calculate. And again, the units, we can't forget those, grams per mole. Okay, because we're going to learn down the road here fairly soon, if you haven't read about it yet, but we're going to use that molar mass because, like I said, we can write it as a ratio of grams over 1 mole of barium hydroxide, or 1 mole over 171.35 grams for barium hydroxide, okay? And that could be used in our calculations. We can write that ratio one or two ways. Okay, so when it comes to calculating molecules, remember Avogadro's number. Avogadro's number is a big, big number. That also is a ratio. That's all we got here, nothing but ratios that we're going to be utilizing. And those ratios can be written in two ways, as I demonstrated with the molar mass. And so Avogadro's number is simply a number, a count for anything, just like a dozen is 12. Avogadro's number is 6.02 times 10 to the 23rd. It could be atoms, it could be molecules, it could be ions, it could be bananas, oranges, apples, or whatever you're counting. That's a number. And the denominator is moles. So there are 6.02 times 10 to the 23rd units. Use the generic units per mole. Okay. And every mole has that number. And being a ratio, I can write it as shown here to the left and shown to the right, one or two ways. Which one I need depends on the question that I'm being asked. So here you're being asked the question, how many calcium atoms are in 0.25 moles of calcium? Okay, well, I always write down what I've been given and what I'm looking for. They're asking you how many atoms, how many, okay? All right, and this is what I'm given. I have 2 moles of calcium, 0.25 moles of calcium. So I write that down. That's what I'm given. Moles of calcium. Okay. And if I also write down what I'm looking for, atoms of calcium. So I can keep track of my setup so I can make sure I set that up properly. Now let me rewrite that because it looks like that little a here looks like it's a capital A, and obviously that's incorrect. Lowercase a, calcium. So I have a conversion factor that I need to put in here. And obviously the way I wrote it is I want moles to cancel. Therefore, that factor has to have moles in the denominator and atoms in the numerator. Okay. And that is what Avogadro's number is. So that is how I'm going to use Avogadro's number with its number in the numerator, 6.02 times 10 to the 23rd per 1 mole. I check, my moles cancel, leaving me behind units of atoms. I set that up properly. Okay. Let me give you the print. And so here I go. There it is. You can see that my moles cancel here. Okay. And I type in 6.025. And then remember, I got to use scientific notation to put that into your calculator. Please do not say, do not type it in like this. You type in 6.02 and then you hit the times button. And then there's a button that is 10 to the X power. You hit that. No, don't do it that way. You're not going to have the right number. Remember, scientific notation, one of 3 buttons. You either have a button labeled double E or a button labeled EXP, or the newer ones out there have a button that are labeled with, I believe it has an X up front and then a little X times 10 to, oh yeah, I remember now. Hold on, let me redraw that. Okay, there's a button that has a times table, X, and then 10 to the X, okay? Not the top button that has by itself just 10 to the X, not that button, not that one. So all these 3 buttons, depending on your calculator, it could be a primary button or it could be a second function to check your calculator. So with that being said, I type in 0.25, hit the times table, and then type in 6.02, then hit one of those 3 buttons, and then type in simply the 23, and that gives you inputted that number into scientific notation into your calculator, and then hit equal. Okay. Your calculator may display your answer like this with the E, and then maybe 23. Okay. Hold on 1 second. Somebody wants to come in. All right. As I was stating, your display would be something like this, where this is not scientific notation, converted into that format. Okay. All right. That's a quick review on your scientific notation of your calculator. Second question. Here you're being asked to calculate the moles of 3.75 times 10 to the 27 molecules of oxygen. All right. So now we want to get moles. Okay. If we start off with this number, molecules of oxygen. So I write down what I'm given again, 3.75 times 10 to the 27. And this is molecules, shorthand for molecules, MLCS, molecules of O2. Okay. I know I need a conversion factor here of some sort. We'll figure out how to set that up here in a second. But then at the end, I'm looking for units of moles of O2. Okay. So that tells me that molecules have to be in the denominator and moles have to be in the numerator in the conversion factor. So it looks like, obviously, that I'm going to need Avogadro's number in that manner, with moles on the numerator and 6.02 times 10 to the 23rd. Note that my molecules cancel, okay, leaving me units of moles. This is what I'm looking for. So now you're gonna be dividing some big numbers here. So you're gonna use scientific notation, type in 3.75, hit your scientific notation button, input the 27. Now you hit the divide button and type in again 6.02, hit your scientific notation button and then input the 23 and then hit equal. Okay. Having done that, your answer should be 6,230 molecules of oxygen. Okay. Now, a question about the significant figures here. They really don't play a role here. Think about this for a moment, because you're given 3.75 times 10 to the 27 molecules. That's a whole number, okay? Because it's not really a fraction, 3.75. You got to move that decimal point over 27 times. And so that's a humongous number. That's a whole number. And you're dividing by another whole number. And so technically, whole numbers, you don't have sig figs. So if you put in 6230, just put in as many decimals you can put in and then see what number you get and just put the whole thing in there. You should end up with a whole number of some sort. Okay. So it's not like I got to put 3 sig figs because 3.75 is 3 sig figs. If that were a measurement, okay, I can understand that, but that is a measurement of an exact number, the count number. Okay. All right, give me 1 second. Okay. And so here, you're going to have a number of questions. We are going from grams to moles. Okay. Right now, what we did is go from molecules, atoms to moles, moles to molecules and atoms. But now, with that information, we can also go to grams. Because think about this for a moment. When you're in the lab, you're not actually measuring moles. You have a balance. It weighs out in grams. Most of the units, grams and metric units. And so we need to convert those molecules into moles, and then from moles convert into grams based on the molar mass of whatever you're trying to calculate. And the important lesson here is that if I want to go from apples to oranges, and I use this a lot, is I need to go through a unit that is common to both. And this is the unit. The unit is moles. I cannot get from compound X to compound B without going through moles first. And we're going to utilize that concept quite a bit, especially in the next chapter when we start doing calculations from balanced chemical equations. Okay. All right. So here we're going previously. Let me stop that. Here we went from we first learned to calculate the molar mass, and I emphasize the fact molar mass has units of grams per mole. Okay. And then we took Avogadro's number, which has units of what? Atoms, molecules per mole. Notice the common factor they got. The molar mass has grams per mole. Avogadro's number has units per mole. Okay. And then we're going to have balanced chemical equations that have a mole ratio to get from point A to point B. All right. So moles are very important in calculation. So here they're asking you the question. First question. How many grams is 1.667 moles of oxygen gas? Okay. Here's the question. Well, let's break down the question because there's a few things that you hopefully know by now. One, the question says oxygen gas. All right. That means we're talking about diatomic oxygen. not just oxygen. If it would have said the oxygen atom or just plain oxygen, then we're talking about one molecule, one atom of oxygen. But oxygen, as we know, is one of the 7 elements is diatomic, and they're gases. And so we are talking about O2. Well, what does that do to the molar mass? It doubles it, correct? Because now we have a molar mass of 32 grams per mole. And if you didn't remember that this is diatomic, you be using the number 16 for one oxygen. So that's important. We have 1.667 moles of oxygen. We want to know how many grams that amounts to. Okay. So as always, we write down what we give. 1.667 moles of O2 gas. Okay. And obviously we're going to have a conversion factor here of some sort because we want to get to grams of O2. Okay. And what we're utilizing is the molar mass. So that means that I want to get rid of moles. So obviously moles is going to be in the denominator and grams will be in the numerator. Okay. So we got 32 on top, 1 at the bottom. Okay. Back to your units, moles of oxygen gas cancel. Now it's a matter of multiplying moles by the molar mass to give you grams, which now hopefully you can see something here that when you start with moles of anything, and if you multiply by the molar mass of that material, you get grams of that material. Okay. Let me repeat that again. If I have moles of an element, a compound, or whatever you're working with, and I multiply by its molar mass, I get grams. See my units, I end up with grams here. So what does that mean about the converse? That if I start with grams and I divide by the molar mass, guess what I get? Moles. Okay. All right, so that's how we set up that problem. Now I won't show you the answer right now because I don't have them separated. So we're going through each one and how we're going to set that up, and then I'll show you all the answers. That's how we did the first one. Write down what we have, write down the units we're looking for, then we have a conversion factor. Okay. Now get used to this system because you're going to eventually get 3 conversion factors back to back to get from point A to point B. Okay. And keeping track of your units will allow you to get through the calculation. Some of these questions may look very complicated and difficult. And of course, you know, it's the first time you've probably seen them. That's okay. But my way of attacking difficult problems is to break it down in pieces. That's what you do. You break it down in pieces based on what you know. And you'll see that small pieces, breaking them down and putting the whole thing in small pieces, you solve the problem, this complicated problem. Okay. All right. The bottom line is this: with the tools you have now, with the tools and information that you've been given, and some practice, and using a stepwise systematic approach, you should be able to attack whatever problem is given to you. Okay, as difficult as they may read and look like, but it really doesn't. It really is not that difficult. Okay. Okay, let's take a look at the next one. So next one, number 2. How many moles is 45 grams of silver? Okay, 45 grams of silver. So we're going from moles to grams. So that suggests that we need to find the atomic weight of silver. And that is, I'm having it, where is it? Where are you going to find it there for a second? Silver has an atomic weight of 107.87 grams per mole. Okay. Now, if you remember what I said earlier, I got grams. I want to go moles. What are you doing? Yeah. Remember what I said? Well, if you don't, let's break it down. Write down what you have. 45 grams of silver. Okay. We know we have a conversion factor. Okay. We want to get to moles of silver. You can read. Okay. Okay. 1 minute. Okay. And so we have grams, we want moles. So let's set up our conversion factor here. The units only. Notice I haven't done anything with the numbers. Now, eventually, as you take this systematic approach and you become familiar in how to, you're eventually going to go right through the problem and figure it out and set it up properly. But until such time, take it stepwise. Okay. So we know that we want grams in the denominator and we want moles in the numerator, right? And how do we know? Why do we know that? How do we know that? Because we know when we multiply this out, we want the grams to cancel out, right? Leaving us with units of moles. And we know that from the atomic weight of silver, it's 107.87. So I know you may be tempted to take the inverse of that number and dump it in here. Don't do that. It would just make things worse. Sometimes it can, if you take the inverse of that number, you end up with a fraction and then you use that number. Throw in the whole number right there, just like I got it. That way, there's no question. I've seen so many errors have occurred by doing that. So just throw in the whole number like it is. Okay. 107. So you can see that if I have grams and I want moles, guess what? I'm dividing by the molar mass. Okay. Leaving me with units of moles. All right. So that's how we set that one up. Let's work on the next one. Here they're asking you, if you start off with 0.55 moles of water, how many grams of water do I need? Do I have? Okay. So again, we got water. Well, we need the formula, right? We were fortunate here. This is just the element. There's no formula involved. We knew that oxygen was diatomic, simply O2. Water, obviously, is H2O, if you didn't know, but you might want to commit that to long-term memory. The molar mass is 1 oxygen, 16, 2 hydrogens at 1.01. Okay, so it's 16.00, and that's 2.02. We have a total of 18.02 grams per mole. Imagine that. 18 grams of water, and you have 6.02 times 10 to the 23rd molecules of water. That's a lot of water, huh? A lot of molecules. So there's the molar mass. Okay, as always, we write down what we're given, 0.0554 moles of H2O. Okay, obviously I'm going to need a conversion factor here. And based on the question, we want to know how many grams of H2O we have with 0.055 moles of water. So grams is in the numerator, moles in the denominator, and that's how we plug in the numbers now for the molar mass, which is 18.02 for 1 mole. Okay, so now we start with moles, we multiply by the molar mass, we get grams. Okay. And that's how we set that one up. Now, finally, the last one. How many grams is 4.75 times 10 to the 16 atoms of potassium? Okay. So we're able to somehow measure out 4.75 times 10 to the 16 atoms of potassium. It's a lot of counting. And we want to know, well, how much does all that weigh? Okay. So let's figure it out. So let's write down what we need, what we have. Given the fact that we're dealing with atoms, should flag you to say, okay, I'm thinking I need to use Avogadro's number. Okay, so, and that is, in this case, atoms per mole. 6.02 times 10 to the 23rd atoms per mole. Remember, it's a number. Units could be anything. Here, the problem says atoms. Like replace units, put in atoms per mole. So we're going to need that. And what else? Well, that gets us into moles. Okay. Remember, to get from point A to point B, I got to go through an intermediate, which is moles. So Avogadro's number gets me into moles, but it doesn't give me into grams. So I need something else. I need the atomic weight of potassium, which is 39.10 grams per mole. Okay. So that would definitely get us into grams now. Look at the common factors here: moles, grams per mole, atoms per mole. The common factor is moles. Okay. All right. So we got all the units we're going to use. Let's put it down. And what do? As always, 4.75. We write down what we're given first, times 10 to the 16 atoms of potassium. Okay. And it looks like we're going to be using two conversion factors here. And to get us to grams of potassium. Okay. Grams of potassium. All right. Well, the first one you can see, we're going to have to use Avogadro's number. Okay. So we're going to put atoms in the denominator and moles in the numerator from Avogadro's number. So we're going to have to take that number and first divide it by Avogadro's number. And that will give us how many moles of potassium. Okay. So we're at that common factor now, moles. Now I can go from there, I can go any multiple directions. Here I need to go, based on the question, to grams of potassium. And so here I need the atomic weight. And so the atomic weight was simply because I want grams in units as grams over moles. I want my final units to be grams. So I want grams in numerator, moles in denominator. So that's 39.10 grams per 1 mole for potassium. Okay. Notice my units cancel out all along. Okay. You should only have one unit. I get occasionally at the end that people put in grams per mole here, and we're looking for grams. That's it. That would be incorrect. Okay. You're all those units other than grams get canceled. They cancel out in the mathematics. All right. So that looks like it's set up properly. Units checked out, everything is good. I set that up properly. Now it's on you to type in the numbers and get the right answer. Okay. Now, I have one thing to mention. I'll wait, say anything later on. So let's see what happens here. Okay, so the first one, we essentially, again, recognize that we have a question. 10 point, 107.8. Oh, yeah. Yes, you're right, Christina. For silver. Is that the question you had, Christina? Or did I write the wrong number down? I may have written the wrong number down. Okay, but you are correct. Yeah, okay. All right. Thank you. Yeah, I wrote that the wrong atomic weight, I guess, for a silver. I was looking, what was I looking at? I didn't know what I was looking at. I looked up quick. So I got my periodic table up here on my desk. Oh, okay. All right. Okay, so it all set up. We got 53.34 grams of oxygen if you have 1.66 moles of oxygen. Okay. And then 45 grams of silver corresponds to 0.42 moles of silver. And 0.055 moles of water represents, it weighs 0.998 grams of water. It weighs 0.998 grams. Okay. Now, the interesting one is that last one, because it gives you a perspective as to how small these atoms are. Okay. Because you have a large number of atoms. But take that zero, move it over 16 decimal places. That's big. That's a lot of atoms. Okay. 4.75 times 10 to the 16 atoms. We divided by Avogadro's number to get us to how many moles that represents. Okay, that's the first factor. Okay. And then we multiplied by the atomic weight, because we know that there are 39.1 grams per mole. And that means that for that number of atoms of potassium, it only weighs 3.09 times 10 to the negative 6. That's tiny. Most balances in the lab can't weigh that accurately. That's small. And so if you put that in perspective, you have this large number of atoms. And even with that large number of atoms, they weigh such a small amount. Okay. And so that means, wow, those atoms of potassium must be pretty small. And yeah, they are. I was asked a question once, have we ever seen atoms? Okay. I don't know if I presented this here, but the answer to that is maybe, not maybe. We have images of atoms. Okay. We have not been able to take one, look around, look at it and inspect it. We have an instrument that is called STM, Standing Tunneling Microscopy. That was actually created by IBM way back in the 80s. And I had the pleasure to kind of research it a little bit. Didn't do too much with it. But at that time, it gave us images of, I think it was gold. It was gold atoms. And it obviously, it looked like you're looking at a poor resolution image of something. You did see the humps and you can see the circular shape. Now, since then, it's gotten a lot better. The instrument has been perfected, more resolution. We're getting a closer look at things. Still, the resolution is not the best, but you can really see a lot. They're using it to find the structure, a lot of polymers, conducting polymers, and which is pretty slick. So yeah, we send images of atoms. Okay. All right. Now, we have something called the molar volume. And this occurs only at specific conditions for gases. Okay. Now we're going to learn in chapter 16 that we can do this calculation for other than these conditions. But for right now, this is true for only under these conditions that are called STP, standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere pressure. Okay. And we are right now roughly 1 atmosphere, and there's some fluctuation. You know, you hear about it. There's a high pressure coming in, low pressure coming in, but we're approximately 1 atmosphere here. Obviously, as we go up the mountains, like up in the high mountains of Colorado, less air, less atmosphere, that value gets smaller. You know, and if we get down into the ocean, we get a lot of pressure on this atmosphere. Well, we call it pressure. It gets high. So anyway, at 0 degrees Celsius and 1 atmosphere pressure, this relationship is true. That 1 mole of gas occupies a volume of 22.4 liters. Remember one of the properties of gases way back when in the earlier chapters, he said, well, gases really have no volume. They occupy the volume of whatever container they are, right? Well, now we have a way to, a condition that tells us the exact volume it has for 1 mole. But again, only true at 0 degrees and 1 atmosphere. So if you take a mole of these gases that are displayed in the first column, all these are gases, and we have 1 mole of all of these, obviously they have in common, you know, Avogadro's number, 6.02 times 10 to the 23rd. Molecules of whatever gas we're dealing with. But because they're different atoms, obviously they have different number of protons and electrons and neutrons. They're going to have a different molar mass. And so hydrogen has a molar mass of 2.02 and so forth. Okay. It just stands to reason they're going to have a different molar mass. But at 0 degrees, they all have in common is this: they all occupy the same amount of volume, and that is 22.4. If I have 1 mole of hydrogen, 1 mole of fluorine, 1 mole of ammonia, 1 mole of xenon, and 1 mole of methane gas, or any other gas out there, all of those are going to have a set volume of 22.4 liters. And guess what? We can use that to do calculations. That's another ratio, okay? Liters per mole or moles per liter. We can utilize that. But the key part to remember is STP. If it doesn't state STP, then this is not true, 22.4 liters. You have to use other equations that we won't know about until chapter 16. Okay. So how do we utilize it? Well, just like we've been utilizing Avogadro's number, just like we utilized the molar mass or atomic weight units, use it very similar. You know, depends on what units we're looking for. So this is stating what STP is: 0 degrees Celsius and 1 atmosphere. Okay. 1 mole of any gas occupies a volume of 22.4 liters. The other aspect is this: that value, the 22.4 liters, keep this in mind. That's a measurement. Okay? Not exact. Okay? Not exact. It's a measurement. And so that last number there is open to errors in measurement. Therefore, this number could be a factor in your calculations with respect to sig figs. Okay. All right. So keep that in mind, that it could be a factor. with respect to calculations when you're trying to determine the number of significant figures. Okay, so how do we use it? Well, here we go. As we've been doing the problems, they all have a central theme here. Systematic approach. Write down what you're given, write down what you're looking for, and then you put in the factors to get me to what I'm looking for. Okay. And so here's our conditions. We are at STP, so that's a factor that we can utilize. First question says, what is the volume of key point? What is the volume? And so obviously we're looking for volume and probably liters, because we are dealing with liters per mole of argon gas here. If we start off at 0.125 moles of argon gas, so we write down what we're given. Of argon gas, okay? Well, obviously we need a factor here. We are at STP, so we can utilize the 22.4 liters per mole. We want moles in the denominator, right? And we want liters in the numerator. Okay. Remember that whole number is also a fraction if I do that. So that helps you out. Okay. We want liters in the numerator because that's what we're looking for. Okay. So now it's to simply plug in the numbers. And there you go. You just do the math, 1.25 times 22.4, then it gives you the number of liters, okay? Note there's 3 sig figs at 1.25 and 3 sig figs at 22.4. So we're gonna have 3 sig fig answers. All right, let's set up the next one. We'll come back. How many moles is 30.4 liters of oxygen gas? Okay, so we're write down what we're given, 30 liters of O2. Okay, we want to know how many moles that represents. And we are at STP. So then we set up the problem with liters in the denominator, 22.4 liters. Why? Because we want liters to cancel, leaving us with moles. I know I sound redundant, but I can't. The more I say it, hopefully it'll stick, okay? All right, so now let's set up. That looks, number 2 looks like we set that up properly. Units look okay, and the math now is on you, okay? Also, too, look at the answer. With the mathematics that you're doing, look at the answer. What type of number you expect without actually doing the math. So it's to see that when you actually multiply or divide whatever, the number looks reasonable based on the mathematics done. Okay, now we're asking a little bit different. Looks like we got an extra step we need to do. All right, so we're still at STP, so we're good with that 22.4 liters per mole. But this time they're asking us for the mass. Oh, chlorine. Okay, if we need the mass, think atomic weight, molar mass. So I got 35.45. Okay, times 2 got 10, 9, 10, 70. Okay, grams per mole, because chlorine gas is diatomic, right? Cl2. Each one is 35.4. Okay, and so it looks like the atomic molar mass is 70.90 grams per mole. We're going to need that. We're at STP. Let's write down what we're given. 40.05 liters of chlorine gas. Okay. we need to get to moles, right? Because to get to mass, which is grams, we need to find that common factor, which is moles. We're in liters. That means we can use the 22.4 liters per mole to get rid of the liters unit. Okay, so at this point, I would have moles of chlorine gas. And then one more factor, obviously, excuse me, I need to get to grams of chlorine per mole. So that's 70.90 grams per 1 mole. My moles cancel. Now I'm left with grams. This question, how many grams of chlorine gas? Now you just do the math, plug in the numbers, and see what you get. But let me clean up my mess and bring out the other ones and see what happens here. All right, so here's the first one. Now, what I said earlier, when you look at the mathematics, the answer, does it make sense based on the mathematics of what you did? Okay, because we know based on this condition that in 1 mole, you're going to have a volume of 22.4 liters, right? We get that. We start off with 1 1/4 mole more, 1 plus a quarter more, 1.25. So our answer has to be greater than 22.4. And so, yes, that number looks consistent, 28. If that number was less than 22.4, given the mathematics that you're doing, that's a flag to tell you something doesn't look right. Okay. So that's what I'm talking about by looking at your answer. Just because you plugged it in the calculator and you think, you know, a number, that calculator tells you a number, go one more step. Make sure, you know, verify that number. Does it make sense? Is the question. Does it make sense? Okay. So is the answer, I should say. All right. By that same scenario we just looked at, number 1, go the other direction. If I have a volume and I'm at STP, that should give me some idea what the moles should be, right? Well, think about this. We start off with 30, over 30 liters of a gas. And we know that in 1 mole, it's 22.4. And so our answer should be close, it should be greater than 1. And sure enough, 1.36, right? Which makes it consistent. Looks okay. And we know we would get a number greater than 1 because we're taking a numerator that is larger than the denominator. So our answer is going to be greater than 1. It should be greater than 1. And so if you get a number that's less than 1, you want to, take a look at that. Maybe you pushed the wrong button. All right. So then finally, you end up with, if you have 4.5 liters of chlorine gas, that's going to weigh 14.2 grams. Okay. 14.25 grams. All right. So this flow chart kind of summarizes these type of calculations, and we're going to have another flow chart down the road, which is even gives you more information when it comes to reactions, and really should be studied and learn how to use it. But this is your direction. This is your map on how you want to get from point A to point B. Okay. And if you use it every time you do calculations, follow this map, you won't have a problem. All right. All right. But the key thing is to remember, look at this. What are we going through? We're going through moles. We start off in grams over here. We be in atoms or ions, or we could be in some volume. Oh, Can't see that color. Let me change it. We could be in volume in liters. And like I said, we could be in grams, or we can be in counts of atoms or whatever. Now we can go in every direction from here. We cannot, let me restate this. We cannot go directly like this. Cannot do that. Cannot do that. Cannot go direct. Okay. We all have to go through moles. And we can go from grams to moles to volume, or we can go from volume to moles back to grams. And the same true, we can go from atoms, ions, molecules, formula units, whatever, to volume, but we could go through moles and vice versa. Or we can go directly from, not directly, from grams to molecules. Hey, that's a big mess here, huh? But you can see, let me clear it up a little bit. Double arrow, double arrow, double arrow, okay? But we cannot do anything unless we go through moles. And this is going to be true when we get to this part, when we start doing calculations of reactions, okay? So, and what I like to say is I can't get from apples to oranges unless I go through moles, okay, to correlate the two. Yeah, so, keep this chart for a flow chart for a reference. All right, so here we have how many grams does 17.35 liters of neon gas mass at STP. All right. So if we have 17.35 liters of neon gas, what does it weigh? That's what they're asking. Okay. And so now you got the answer here. But again, I write down what I'm given and what I'm looking for unit wise. I got 7.35 liters of neon gas. Okay. I am at STP. And so that being the case, I can use the 22.4 liter relationship for 1 mole because I am at STP based on the problem. That gives me into moles of neon gas. And then using the atomic weight or of neon gas, which is 20.18 grams, now I get to grams. Okay. And notice again, my units cancel out, leaving me with grams, which is what the problem asked for. Now, then they ask a second part. They say, how many atoms is this? All right. Well, again, I write down what I'm given, 17.35 liters. All right. I got to get to atoms. So that tells me I'm going to be using Avogadro's number in here someplace. All right. So the first unit, I put in 22.4 for the volume. Okay. Because I'm at STP, that cancels out. Hold on 1 second. Okay, liters and liters. And then I got moles and moles that cancel out, leaving me with atoms unit-wise. I can't overemphasize using this technique, this procedure with the conversion factors. I know you're going to be tempted to want to use ratios a different way. And I'm telling you that I find too many errors involved in using that. Also, too, for example, let's take the bottom question. Let me clear this up a little bit. This type of question, maybe it's something you need to submit or write in or type in. And we may break this question up. For example, this question may be worth a total of, I don't know, 4 points. Total 4 points for the last part, okay? But we break it up and we generally give 1 point for the answer. And then the other 3 points is for how you set this up. So when we talk about showing work, we talk about this scenario, okay? And yes, I know you can do it, and I know you can type it in and just report your answer of 4.66 times 10 to the 23rd, and that will be correct. However, you only get 1 point if you don't show any work, okay? So do show your work to get the full credit. Now, this also works in the other direction because you should not be penalized because you may have set the problem up correctly. You understand the question, you understand what the answer is, but for some reason, you may have typed in the wrong number and that answer is incorrect. Whatever answer, maybe you typed in 5.30 times 10 to the 22. Maybe that's what you got. Obviously, that's not the right answer, but you set it up properly. Well, you'll get the 3 points because you set it up, but you won't get the 1 point because your answer was calculated wrong. Okay, shouldn't be penalized for knowing how to set that up and just messed up because you typed it in wrong and calculated wrong. Okay, so if the question doesn't say don't show your work, yes, of course, you just give your answer, you're good to go. But if it does say show your work, that's what we're talking about. Showing us how you came about to get your answer. Okay. Which brings us to density. Okay. And we did talk about density, I believe we did a while back, where we have mass over volume, another ratio, right? Well, the cool thing about working at STP and gases, you can calculate the density of gases at STP where you don't even have to measure anything. Because obviously the mass over volume, most of the time you measure the atom, measure its volume, and you got its density. Well, being at STP, you know that the molar volume is 22.4 liters per mole, right? And the molar mass, well, you simply add up the atoms, and guess what? When you take the molar mass and you divide it by the molar volume, you got density, okay? And so that's what you got here. Now, you have 17.04 grams per mole. That is the molar mass of ammonia, NH3, 1 nitrogen, 3 hydrogens. And we know we're at STP, so 1 mole occupies a volume of 22.4 liters. So therefore, when you do the math, moles cancel out, and you end up with units of grams per liter, which, by the way, is mass per volume, okay, or AKA density, okay? All right, so very straightforward. If you need to calculate the density, the density of any gas at STP, you simply divide the molar mass by the 22.4 liters per mole. We're almost done. This is called percent composition. All right, we talked about calculating the molar mass, and what we did, just to repeat, was we add up all the atoms of all the different atoms, who add up their atomic weights and how many of them, contribute to the overall formula, and we tally it up, we add it up, and we come up with the molar mass. But we can also calculate the percent composition, okay, simply by taking the contribution of each atom to the whole molecule and dividing by the molar mass of the whole molecule times 100, and you get a percentage, right? All right, just like your grade is calculated, you got a total points, but there's a percentage of coming from each of the different sections of your homework. All right, take for example, water. Water, as we talked about earlier, has a molar mass of 18.02. That's the molar mass of water. Now the hydrogens, there's 2 of them. It contributes a total of 2.02 grams. So 2.02 divided by 1802 times 100 gives us the percent composition of hydrogen in water, which is 11.2%. Okay. Now, if you do the same thing for the oxygen, there's only one oxygen. It's 16 grams divided by 18.02 times 100. Then you get the contribution, and all that should add up to be approximately 100%. Normally, that one probably, that should be 88.8, for example, would give you 100%, but everything should add up to 100%. So this means that water, H2O, if it were analyzed, if you had a liquid, we analyzed it, you will find it to have 11.6% hydrogen and 88.8% roughly oxygen. And that would be true for water we obtain here in Arizona, or water obtained in Alpha Centauri, H2O. That's the percent composition. Okay. All right. With that being said, does anybody know by chance? Here we got a percent composition example. But it says here, find the percent composition of TNT. Does anybody know what TNT is? I'll give you a hint. It makes a loud noise when it's ignited. It could be very destructive too. It's AKA dynamite. Okay. That is the structure for dynamite. Yeah, there you go. Dynamite. Now, let me ask you a little side note. You know, it's a little bit of side note. Does anybody know who discovered dynamite? Very famous guy. He is, there are prizes given out every year in science, in peace, literature, medicine. Alfred someone, there you go. Yeah, it was Alfred Nobel, that's correct. And in fact, he made a lot of money with the discovery. In fact, enough money that there's created a Nobel organization, and pretty impressive. What impresses me is this compound from an organic standpoint. Me being an organic chemist is very sensitive to make. I've had an explosion in my lab before, not because of this, it's some other thing. And it was a small explosion, and this stuff, it carries a lot of power. So, and to make it is very specific. Basically, anyway, it's got three what are called nitro groups, the NO2 groups around that compound. Well, anyway, there's the formula, general formula, and that is C7H5NO2. Okay, there's three of them. And just as a side note, let me just give you the structure. There are chemicals, compounds that have 6-membered groups, and each point there represents a carbon. And this particular, there's double bonds, alternating double bonds. Okay, that's the base compound. And then there's a carbon coming out with 3 hydrogens bonded to that carbon. That is the toluene group. And then they got the 2 nitro groups like this. Okay, bonded around there. And that's basically the structure of TNT. Very fancy. I know we don't talk about organic chemistry, but it's not too bad to put in the first 2 nitro groups, but sticking that third one is very challenging. These things tend to go boom. All right, so what we need to do is calculate the percent composition. So what do we need? We got the formula, okay? Based on the formula, now we calculate the molar mass. Well, no different than we've been doing before. We use, well, first of all, be sure you use the periodic tables that we supply. Okay, carbon has 7, there's 7 carbons. Each one has an atomic weight of 12.01, so that's a total of 84.07. 5 hydrogens, each at 101. Okay, it's a total of 505. Nitrogen, there's 3 of them. Okay, so that's 1401 for each one. That's a total of 4203. Then there's 6 oxygens, and that's a total of 96 grams per mole. Tally all that up. TNT has a molar mass of 227.15 grams per mole. Okay, grams per mole. Now, to do the percent composition, you simply take the atomic weight, the total mass of each element that contributes to the total compound, divide that by the total molar mass times 100, and you're good to go. Okay. And so carbon represents 37.01%. Okay. Hydrogen is 2.22%. And nitrogen is 18.5%. And then at the end, you got oxygen at 42.26%. Okay. So, and we do this all the time with respect to compounds. As an organic chemist and making new compounds, after I cleaned them up and purified them and got them all constant as far as the weights, I would send samples out, ask for carbon, hydrogen, nitrogen, sulfur, any other element that we look for. And then when the report comes back, it will give us a number percentage like given here. And we can take that percentage and back calculate to an actual general formula. And so that would verify that based on our other data that that's the compound that we have created. Okay. So anyway, try these at home. Good time to bring them in next Friday. You know, when we got after we finish that chapter, we're going to have a lot of time left over. So try these at home. How many liters will be 3.425 grams of carbon dioxide occupy at STP? You should come up with 1.74 liters. Second question is, how many molecules are in 3.425 grams of carbon dioxide? You should end up with 4.60 times 10 to the 22 molecules. And then the last one says, how many grams would 3.02 times 10 to the 15 molecules of carbon dioxide mass? How much would it mass? That's a lot of molecules, but yet, look at that weight. It's small. 2.2 times 10 to the -7 grams. Right? -7 grams. All right. All right. Well, congratulations. You are officially done with chapter 12. What I'm going to do is let's take a little 10-minute break. Then we'll come back with chapter 13 and we'll go through that one. Okay? All right, we're back. Now, this particular chapter deals with stoichiometry. Okay, it's a term that basically, you know, we've been balancing equations. We have the coefficients that we come up with. Those coefficients in front of the molecule, the formula of the compound, tells us how many of each reactants, for example, are necessary for this reaction to proceed. Or it also tells us how many, if we start off with X number of reactant, how many products are we going to get? Okay. For example, let's take a look at these couple of reactions here. We have nitrogen monoxide reacts with oxygen to give us nitrogen dioxide. Okay. Now, Balanced chemical equation. Let's make sure it's balanced. I got two nitrogens on the reactant side, two on the product side. I have a total of 4 oxygens on the reactant side. 2 of them is NO, 2 of them is oxygen. And on the product side, I have a total of 4 oxygens. So yes, we are balanced. Now, when we look at this, we say, well, if 2 molecules of NO react, I need 1 molecule of oxygen because it's understood, if there's no number there, it's understood to be a 1, okay? And that reaction proceeds, we will get 2 molecules of nitrogen dioxide. Now, if we increase the amount of, let me mark this. If we increase the amount to say 10 molecules of NO, well, you can see here that we need at least, at the minimum, 5 molecules because the ratio is 2 to 1. It's understood to be a 1 here again. And so that means that if I start off with 10 molecules of NO, I'm going to need at least 5 molecules of oxygen, which then would produce 10 molecules. Now, I can start with 10 billion molecules of NO. Well, that means I need 5 billion molecules of oxygen, which will produce 10 billion molecules of my product. Okay, so that ratio is true whether I have a simple 1 molecule at whatever number of molecules I need. Now, we don't talk about molecules here. We actually talk about moles. So what really we should be saying is, if I start off, I need 2 moles, okay? 2 moles, that's 6.02 times 10 to the 23rd times 2 of those, okay, of NO to give me 6.02 times 10 to the 23rd moles of oxygen, which then will give me 2 moles of fire, okay? That's what those coefficients are telling us. And that's why it's so important that we make sure that we are balanced. You always have to balance your chemical reactant. Otherwise, if we assume it's a 1-to-1, then you can see that we're totally off if we're going to do any type of calculation. The next one is nitrogen in the presence of hydrogen gives us NH3, which hopefully you're familiar with by now. It's called ammonia, okay? After balancing, it shows that I need 1 molecule of nitrogen, but I need 3 molecules of hydrogen gas to give us 2 molecules of ammonia, okay? So another way to look at that, because sometimes the coefficients confuse people, is, well, there, I got 1 nitrogen molecule, okay? And in fact, let me do it this way. I got 1 nitrogen molecule. Yeah, just do it like that. But I need 3 molecules of hydrogen. And what that does is gives me 2 molecules of ammonia, okay? So I got 2, 4, 6 hydrogens in the reactant side, 6 in the product side as ammonia, 2 nitrogens in the left, 2 on the right, okay? It is still nitrogen. Okay? It still has 7 protons, be it in the form of a elemental or molecule of nitrogen, or be it in the form of ammonia. It is still nitrogen. All right, that's same scenario here, with respect to the moles. All right, so coefficients give this mole ratio. And now what does that mean, this mole ratio? I've always emphasized these ratios. Let me go back to the last one here. We can see here that it's from nitrogen to hydrogen, the relationship is a 1 to 3. So I can write that as a ratio where I got one nitrogen over three hydrogens. That is my mole ratio. And I can write it in that form, or I can write it with the hydrogen in the numerator or denominator, like this. Now, I'm going to use that in my calculations, but it depends on what the question asks for. And again, following my units like we've been doing tells me, like we just did with Avogadro's number and the molar mass, which is also, both of them are also a ratio. This mole ratio, we're going to utilize because at one point in time, you're going to be talking about moles of nitrogen, and I got to relate that to moles of hydrogen. And I do that by using one of these mole ratio relationships, okay? Now, also, and I'm going to change that to a different color so we can see we're talking about a different ratio, is the relationship between nitrogen and product, ammonia. That also has a mole ratio of one nitrogen in the numerator and two in the denominator. Or invert it. Two nitrogens, one nitrogen in the denominator, two ammonias on top, okay? And guess what? We have a third relationship, and that is between the hydrogen and the product, okay? And so that ratio is 3H2 over 2 ammonia, which can be written in the following manner. Okay. And so this simple reaction with two reactants and one product gives us a total of 6 mole ratios that we can utilize in the calculations. Which, by the way, both these reactions, what type of reactions do you think they may be? If I had to classify them. You got 6 types. Okay. Combination, that would be right, correct, Christina. You're getting 2 products, 2 reactants to make one product. Okay, they're being combined. So that's a good example of a combination reaction. All right, so we got these mole ratios that we can utilize, and there's 6 ratios that we come up with a simple reaction. Now, I didn't do it for up here, but it's the same setup here. This relationship there between the reactants, between NO and NO2, that's another relationship. O2 and NO2 also has another relationship. So that too, that example would have a total of 6 mole ratios that I can utilize and set up if I need to use them for some reason. Right. So let's take, for example, this reaction. FeO3. Does anybody want to take a chance? If you don't take a chance, you should know this, right? You're going to work it through. What would be the name for Fe2O3 if I had to name that compound? It'd be this guy right here. Name that compound. You can unmute yourself if you want. Heck, there's only 11 of us here, and I'm one of the 11, so there's 10 of us. Okay, what we got here? We got iron dioxide. What? You got the iron part right. Okay. Now remember, no prefixes for ionic compounds. This is an ionic compound. Prefixes for covalent compounds. And so, yes, this would be called carbon dioxide. This would be called carbon monoxide, but they're covalent compounds. Okay. So the iron is correct, but not the dioxide, and we're missing something. There's three parts here. I'll give you the you're 1/3 correct. Well, let's work it. Since it's no prefixes, then there you go. We got iron 3 dioxide. That's correct. Now, remember, we have to add these together such that they add up to 0. And we know that, there's 2 irons, right? And we know that every oxygen is a -2, and there's 3 of them. So I got a total -6 for the oxygens, and that equals to 0. And so now you have an algebraic equation here that you can solve for iron. And it turns out that iron would be equal to a +2 charge. And what am I saying? +3 charge. I got a mess here. Let's clear this up. If you solve that equation, you would end up with iron is equal to a +3. And therefore, remember, there's only 16 metals that have a constant oxidation number and therefore do not require the Roman numerals. That means all the other metals require the Roman numerals to determine what oxidation state they're in. I also said back then that there's a little help for you, because if you think about it, doesn't the subscript of the anion, which is 3, become if you look at the subscript of the anion, which is the oxide, is the oxidation number of iron. And the subscript of the cation, guess what, is the oxidation number of the anion. Okay. So that kind of quickly, you could at a glance determine it to a quick name, iron 3 oxide. All right. So here we have iron 3 oxide in the presence of carbon monoxide, reacts to give you iron and carbon dioxide. And in fact, this iron 3 oxide is also AKA rust. Okay, so my old truck had a lot of iron 3 oxide in it. But if you treat it with carbon monoxide and a little bit of heat, you're able to break that carbon monoxide down, which is a good way to get rid of carbon monoxide and create carbon dioxide. But you pay one gas for the other. But carbon monoxide is more deadlier gas than carbon dioxide. Carbon monoxide, FYI, for your health people out there, carbon monoxide normally binds to the hemoglobin in your blood system, but it binds irreversible. Carbon dioxide also binds to your hemoglobin, as does oxygen, but is reversible and depending on the pressure of your lungs and so forth. So that's why the hemoglobin, which has, by the way, an iron in the center of it, complexes with the carbon dioxide and in your outer body, in the veins or the out extremities. And then when it travels back into the lungs, pressure change, other things happen. It releases the carbon dioxide, but picks up oxygen and then goes back into the system. So it's an irreversible change. It goes carbon dioxide, oxygen, which is a good system. The moment you stick in some carbon monoxide, messes everything up. It binds to there's 4 oxygen, 4 molecules of gas that can bind to the carbon monoxide. Either all oxygens or all carbon dioxides or a combination thereof. But carbon monoxide binds to it permanently. It doesn't come off, and therefore renders that hemoglobin inactive. And it can't get rid of it until your blood cell dies and gets, be generated, which I think is 90 days or somewhere in there. So that carbon monoxide goes around your blood system till it's destroyed. So forth. So side note there. All right. It's all about chemistry and absorption in our body. All right. So the reaction, as we stated, we got a 1-to-3 ratio between reactants. And guess what? We have a total, you can go through this, a total of 12 ratios here. You know, obviously you got this combination between the reactants, and then iron 3 oxide relationship with iron, okay? And then iron 3 oxide relationship with carbon dioxide, okay? And so that ends up with, what do we got? 2, 4, 6 ratios there. Then we can go with carbon monoxide, its relationship mole ratio with iron, and then carbon monoxide, its relationship with carbon dioxide. So it's 2, 4 there, 2, 4, 6, 8, 10. And then there's even a relationship between the two products. So that's a total of 12 ratios. Okay, that one can work with if necessary. Okay, so you can see how we did that here. You got this relationship here between the two iron 2 oxide and carbon monoxide, which you can write FSO or you can write FSO, depending on what the question asks for. So if we look at the first question, it says, how many moles of iron can be formed if we start off with 10.2 moles of carbon monoxide? Now, with respect to these type of questions, your only concern is what the question is asking about. And so how many moles of iron, which is this, and they want to know how many moles can be formed from 10.2 moles of carbon monoxide. So 10.2 moles of carbon monoxide. Okay. So our only concern is between carbon monoxide and iron. Everybody else, the iron 2 oxide and carbon dioxide, don't play a factor in this reaction. We're only concerned about those two. So our ratio here is 3-to-2 or 2-to-3, depending on how we need to write. So as always, what do? We write down what we're given. We're given 10.2 moles of CO2, okay? We have a conversion factor here that we're going to obviously use, and we want to get to moles of iron, okay? And so by putting down the units that I have and what I'm getting to helps me set up that conversion factor a little bit better, because I need to get rid of carbon dioxide. So that goes in the denominator and iron goes in the numerator, okay? See that? This part comes from the balanced chemical equation. There are 2 irons. The mole ratio between iron and carbon monoxide is a 2-to-3. So guess what? Go back and check your units. Okay, everything's set up, cancels out. Now I just got to do the math. 10.2 times 2 divided by 3. Boom, I got my answer. Okay, so let me clear this up a little bit. Okay, we talked about that. Yeah, so here we go. So if I have 10.2 moles of carbon monoxide were formed, I can back calculate and figure out how many moles of iron were utilized. And that becomes 6.80 moles of iron. Notice here, like I said, I'm not worried about the iron 3 oxide or the carbon dioxide, because the question only deals with carbon monoxide and the iron in that particular ratio. Okay. So let's go through the setup here with Let's give it a blue here. The next question. Next question states, how many moles of iron 3, moles of iron 3 oxide? And so, how many moles of this are needed to form 17 moles of carbon dioxide? And so I'm concerned about, I need to make 17 moles of carbon dioxide, okay? So my only concern is between the carbon dioxide and the iron 3 oxide. Guess what? Check this out. It's telling you I need to make 17 moles of carbon dioxide. That's how much I need for whatever reason. Well, how much iron, how much rust do I need to start off with so I can make at least 17 moles? How much iron 3 oxide do I need to start off? We're not concerned about the other reactants and products, okay? It's assumed that there's sufficient carbon monoxide there to give you what you're looking for. And the ratio there's 3 to 1. And this is how you actually would do it, whether it be 17 moles of carbon dioxide, or you for some reason, want to make 17 million moles. That same ratio would be utilized to do the calculation. All right, so as always, we write down what we're given. We got 17 moles carbon dioxide. Well, obviously, we're going to have a conversion factor here. We're getting 2 moles of iron to 3 oxide. That's what we're looking for. Okay. And so CO2 goes in the denominator. Iron to 3 oxide goes in the numerator. Okay. 3 to 1 is our ratio based on the balanced chemical equation. Okay. 3 to 1. Now, check your units. CO2 cancels, iron 3 oxide remains. I got it set up. I'm basically going to need a third of 17 moles. Here we go. And it's roughly not roughly, it is 5.7 moles of iron 3 oxide. I needed to make 17 moles of carbon dioxide. Keep this in mind now. We're dealing with moles, right? Now, when we add another piece of information, that is the molar mass, remember the units of molar mass, and that's grams per mole. Guess what? Now we can go to grams because we're not measuring out moles of iron 3 oxide. All right, we're measuring out grams. And if carbon dioxide being a gas, and if we're at a certain temperature, guess what? We're measuring out volume because it's difficult to weigh out gas of CO2. We're going to either use STP, because we can calculate have an actual volume, or we can use another method called, measuring the flow rate or something, but that's beyond the point here. All right, but the point there is we're working with moles here. We're going to progress over to get to grams here in a bit. All right, so here we have sulfur dioxide in the presence of oxygen gives us sulfur trioxide. Well, if we balance it out, we end up with 2 sulfur dioxides, 1 oxygen, and that gives us 2 sulfur trioxide. Okay. Let me see here. Now the question here says, how many moles of sulfur trioxide will form if we start off with 0.165 moles of O2? Okay, so we're only worried about O2 and SO3. So as always, write down what we're given. Okay, that's how much oxygen was reacted. And we need to know moles of O2. So we know what direction we're going. So obviously O2 goes in the denominator, right? Uh-oh, what did I do wrong? Not O2. Why nobody caught me here? SO3, sulfur trioxide. How many moles of sulfur trioxide will form? All right, so we know that we want O2 in the denominator and SO3 in the numerator. So SO3, we got a 2 there, and O oxygen, we got a 1. That is the mole ratio. Okay, oxygens cancel, leaving us with sulfur trioxide. So it's twice of 0.165. Okay, which is 0.3301 moles of sulfur trioxide. Okay, here we're asking about how many moles of sulfur dioxide are needed to make 0.042 moles of sulfur trioxide. So we're concerned about those two. So, as always, what we're given. Okay, we have a conversion factor here and moles of sulfur dioxide. So we net the trioxide in the denominator and the sulfur dioxide in the numerator. We can see the coefficients in both cases are 2. So by all means, obviously it's a 1-to-1 relationship. If you see that, you can just go 1-to-1. And the answer here would be 0.042 moles of sulfur dioxide. Okay, did you can see these cancel out? All right, the 2's cancel out. And there you go. So if I need, if I start off with 0.042 moles of sulfur trioxide, I will make the same amount. I would need the same amount of sulfur dioxide. All right, so here's this flow chart. Okay, and there's still one more flow chart. It's going to combine even some more things here in the bit, but it's just it's an added part. Yeah, in the previous flow chart, we were dealing with just the moles. We were in the inner part right here. Okay, but now we expanded. I said we have the molar mass. Molar mass has units of grams per mole. That allows us to go from moles to grams by knowing the molar mass. And so if we have grams given, that is grams that is given to us in the problem, and we know the molar mass, remember we're dividing by the molar mass, that gives us the moles given, okay? So we have grams of whatever it is, we need to convert those grams to moles using the molar mass. It's a chemical equation reaction. So therefore, once it's been properly balanced, we look at the question whether it's two reactants with each other, reactant to products, no matter what it is, it's something to something. It has a mole ratio. That comes from the balanced chemical equation. Okay. That puts us into the moles that we're looking for, what we're finding, what we are searching for. Okay. And once we have that, we can determine the molar mass if we have to of what we're looking for, which then gives us the grams of what we're searching or calculating. Okay. And so in the beginning, we got grams to begin. Guess what? We are dividing by the molar mass to give us the moles. Then we have a ratio of the mole ratio here that gives us moles of what we're looking for. And then once we know the molar mass of what we're looking for, we know the moles, be multiplied by the molar mass to give us the grams. Okay. All right. So, but this is where you're going to be using at least 3 conversion factors. Okay, let's take a look at this reaction here. We have iron 2 oxide. Iron 2 oxide in the presence of specifically 3 moles of iron 2 oxide. Okay, react with 2 moles of aluminum to give us 3 moles of iron and 1 mole of aluminum oxide. Okay. And now, what type of reaction do you think this is? Okay. Anybody want to take a guess here? Or we can do a process of elimination of the 6 types of reaction. Okay, so we can determine what it's not. But let's see, maybe somebody got the answer here. Single replacement. That is correct, Christina. Okay, obviously it's not a combustion reaction, right? We're not burning anything. And it's not a combination reaction because we're not getting one product. Okay, nor is it a decomposition reaction because normally you start off with one product and break that apart. So that's not happening. So we eliminated 3 already. And it's not an acid-base reaction because we'll be dealing with hydroxide and protons and acid. That's not it. And we're not dealing with a double displacement reaction. How do we know that? Double displacement, because you'll find double displacement. The 2 reactants are always ionic compounds and soluble aqueous. Okay, so that removes that. That eliminates the double replacement. So obviously the only thing left over is single replacement, right? Okay. Also, you can see that we start off with aluminum as the element and then gets aluminum as a compound. And then we start with iron as an ionic compound, but then we create, or it generates iron as an element. So yeah, single replacement reaction. All right, so it's balanced. We double check. You got 3 irons on the left, 3 on the right, 3 oxygens on the left, 3 on the right, 2 aluminum on the left, 2 on the right. So it's balanced, so we're good to go. Okay. So we're going to have a couple of questions and we're going to be asked and we're going to calculate here. Let's say it's asking you to calculate the mass of iron 3 oxide needed to react completely with 5.5 grams of aluminum. Okay, so we are dealing with iron 2 oxide and aluminum. That's it. And so we need to know how many. We got 5.5 grams of aluminum. How many grams of iron 2 oxide do we need is the question. The first question. Okay. Okay. Since we are dealing with grams here, guess what? We're gonna start needing atomic weights and molar masses. So you might want to start figuring out calculating the molar mass of iron 3 oxide, and of course aluminum. We can look that up on the in the periodic table. Okay. Second question. There's 2 questions, and we'll walk through it here in a second. Okay. Calculate the mass of aluminum oxide. So here, and that's why it's crucial that, we've been writing names and formulas going back and forth. So it's crucial to identify who aluminum oxide is, right? And it's right here, aluminum oxide. Produced when you start off with 10.25 grams of aluminum react completely. So if you start off with 10.25 grams of aluminum, how much aluminum oxide are you going to make? So the yellow is number 2. Okay. All right. So now we know what direction we're going. Keep this, basically we're going from here to here, but we can't go directly, right? We have to convert everything to a common unit, which is moles, and then the mole ratio converts us to the number of moles of what we're looking for. Okay, and you can see that we need molar mass or atomic weight, molar mass / atomic weight, depending on what the reactants are. Okay, to get 2 grams or to get 2 moles, that's an important part of information that we need. Okay, so now let's work it through. So we have 5.5 grams of aluminum. Okay, first thing we do, we need to convert that to moles. Everything goes to moles. Okay, we're going to apples to oranges, but we got to get through moles first. So this gives me the moles of aluminum. I'm dividing, notice that I'm dividing 5.5 grams of aluminum is grams given. Molar mass, atomic weight, now gives me moles of aluminum. Okay. Keep track of your units, okay, just to make sure. Let me change that color a little bit. See how grams of aluminum cancel out? Now, if I were to stop the reaction, the calculation right here, I would have moles of aluminum. Okay. Now I got to relate the moles of aluminum with the moles of iron 2 oxide. Remember that I am concerned about these two only. Okay. All right. So that ratio is 3:2. Keeping track of my units, guess what? My moles of aluminum cancel. So at this point, I'm now at the point where I've started with grams given, converted to moles given. Now I am moles looking for or find. I need one more conversion factor because the question asked me to figure that out in grams, what the final iron 2 oxide I need. And so I need one more bit of information, and that is the molar mass of iron 2 oxide. Okay. And checking my units here. We cancel. Leaving me with the units of grams of iron 3 oxide, which is what the problem asks. Okay. So with respect to my units, the problem has been set up properly. Now it's up to you to type it in your calculator, and hopefully you should come up with 22.4 grams of iron 2 oxide. Okay, think about it. I want to do that reaction given up on top. I only have 5.5 grams of aluminum. Well, if I want all that to react, all the aluminum to react, I need at the minimum 22.2 grams of iron 3 oxide. Okay. Iron 3 oxide. Okay. Second question, part of the question is that 10.25 grams of aluminum. Okay. We're trying to calculate. Let me clear this up a little bit. We were calculating how much, starting with aluminum, how much aluminum oxide were we going to make? Okay. Aluminum oxide, by the way, is an abrasive material. You find that a lot, sandpaper, all kinds of things. You even find it in makeup sometimes. They use it for you want some wash your face with some abrasive material. In other words, you want to yank that skin off, get rid of dead skin. That's what you're doing, just scraping it off. All right. So first step, as always, we got to convert to moles like we did with the top one. So we got 10.25 grams of aluminum. It doesn't make a difference if it's aluminum. Whatever you started off with, it's given in grams, you've got to get to moles. And so we got to use the molar mass / atomic weight if it's an element to get to moles. Then the second conversion factor gets me into moles of aluminum oxide. And that coefficients come from the balanced chemical equation. Okay. That at this point gives me the number of moles of aluminum oxide. We need to get to grams of aluminum oxide. So therefore, I need to calculate and determine the molar mass of aluminum. Got 2 aluminums, I got 3 oxygens. Its molar mass tallies up to 101.96 grams. Okay. Now, before I do anything else, let me check the units and make sure that everything looks correct. Grams of aluminum cancel, moles of aluminum cancel, moles of aluminum oxide cancel, leaving me with units of grams of aluminum oxide, which is what the question asks. And so now it's set up properly. Plug in the numbers, you should end up with 19.37 grams of aluminum oxide. So if I have enough iron 2 oxide and 10.25 grams of aluminum oxide, I should create 19.37 grams of aluminum. And that is what we call the theoretical yield. Okay. So what that means is this. If I start off and if I was doing this in the quote, real world in the lab, I will calculate that number. And it says here that if I start off with 10.25 grams of this, okay, theoretically, I would make 19, wrong color. Should maybe change the color here. Theoretically, I should make 19.37 grams of aluminum oxide. Okay, that is what our theoretical yield is. But reactions rarely go to 100%. You know, if you're lucky, and you might run this reaction, and you might end up finally picking up 10 grams of aluminum oxide. Well, what you do is you take the 10 grams and divide it by your theoretical yield, okay, times 100, and that gives you the percentage yield that you actually made in the real world. Optimally, you want to be up in the 90s, but you'll find that a lot of reactions are like 15% yield. I had one a fellow graduate student with me that went to work for Pittsburgh Plate and Glass. He helped develop the material that some of you may have glasses that go out and change dark. With that particular material, he helped make it, and he tried to optimize the yield. He had like a 20% yield, but is used a lot in glasses, so good need for it. So they told him to up it up as much as you can, optimize the reaction, which he did. He only got it up to about 5%. And he was disappointed. And he said, I only get it up to 5%. The boss said, hey, don't worry about it. You just earned the company something like $50 million for that 5%. That's when he said, okay, can I get a raise? All right, so those are the examples. And here is the flow chart that kind of puts all those other 2 flow charts together. This is the flow chart, is your map to get from grams given to grams find, okay? You'll notice that to get through all that, you've got to get to moles, and you need molar mass. Now, through the bottom corners, okay, these down here This is only true at STP. Remember that. Only at STP. So if you don't have STP conditions, you can't get to the corners there. Okay. You can't go any further than moles find. Okay. Now, whatever direction you can go. I mean, here it looks like it's one direction because grams given, volume find. Keep in mind, it's a two arrow. You can go from top left corner to the bottom right corner, or you can start at the bottom right corner and work your way back. You just change the given. Same is true if you start in the top right corner and you go to the bottom left corner, or you might just go top right corner to the bottom left corner, for example. Any combination thereof. Well, not any, but you're limited. Either way, you cannot go through anything without moles and the mole ratio of your balanced chemical equation. Okay. So this flowchart really kind of summarizes type of calculations. Okay. And really, if you follow it, and if you look at the problem and you look at the flow chart and just mark on the flow chart where you're at and where you're going to go, definitely will help you to get to that point. Remember to set up your problems in the ratios and follow your units and check off the units as you proceed. And then it's just a matter of doing the math. Okay. All right. For example, we have an equation here. It says write. Let me restate that. We have a problem here and we need to write an equation. Okay. The problem says write and balance the reaction of hydrochloric acid, aqueous, and solid cobalt. Hydrochloric acid and solid cobalt. Then they give you an additional bit of information. They say that cobalt will be in the +2 state as an ion in this example. Okay. So that suggests that cobalt, which is solid, is undergoing oxidation, losing electrons, right? Because it's going to +2 state. So now let's think about this. Let's write down the reaction, at least the part that we have. And let's see, let me change my color here because it's not going to come out very well. All right, let's write down what we have so far. Under telling us HCl, hydrochloric acid, aqueous, reacts with cobalt, solid, to give us something, right? But we do know that whatever that something is, cobalt over here is in the +2 state. So there's a hint. Okay. So how do we can determine what products we're getting here? And so again, there's only 6 types of reactions. Okay. And let's go through a process of elimination. All right. Well, first of all, we can remove the combustion reaction again. Right? Because we're not burning anything here. Eliminate that. Combustion. Combination, can we eliminate that one? Yeah, pretty much so, because normally when we're looking at combination reaction, we're looking at 2 elements reacting to form something. Here, we only have 1 element and the other is a compound, specifically an ionic compound, not ionic, covalent, excuse me. It becomes ionic because it's an acid. Okay, this is an acid here. So combination we can eliminate. How about decomposition? Well, again, decomposition normally starts off with a single compound, and then that breaks down to the elements. So that's not the case here. All right. Well, how about a double? What else we got? Acid-base reaction. Acid-base or neutralization. Well, we have an acid but we don't have a base. Normally a base would be something like sodium hydroxide or hydroxide. So we don't have that. Okay. 1, 2, 3, 4. And then we have a double replacement. Remember the double replacement reaction? Well, normally in the double replacement reaction, the two reactants are soluble in water. So they will both have AQ. Hydrochloric acid is AQ, aqueous, is soluble in water. However, cobalt is a solid. Okay, so we don't have an aqueous solution. So we can eliminate that too. And what is left over? Single replacement. Okay. By that definition, let me restate that. By the process of elimination, the only choice we have is a single replacement. It has to be a single replacement. We went through all the other ones. Yeah. So that means that what? Cobalt must replace hydrogen to do any type of reaction. Okay. And the reaction obviously happened because they're telling us it's a +2 in ionic form. Really, huh? So how's that? Well, go back to where'd it go? Okay. Go back to the activity series. Remember that this activity series was a listing of the reactive metals, right? With lithium being the most reactive and gold being the least reactive. And then, but they're all relative to hydrogen. And I stated at the time, I did mention this, that hydrogen, the ionic form of hydrogen here for activity series is H+. Okay. And so now we can compare cobalt versus hydrogen in what is more reactive. Well, it looks like cobalt is more reactive, right, than hydrogen. And the second part of the question is, is the most reactive material in ionic form? And cobalt is not in ionic form, but therefore reaction proceeds. So by replacing, you see the hydrogen is an ionic form here. We're going to put it back into elemental form, which is hydrogen gas. And we know that cobalt will be in the +2 state because they gave us that. Okay, so the reaction does proceed. And we got chlorides here, and chlorides are, we know also, hopefully, that each one is a -1, the chloride. Started off in group 7. As chlorine, they picked up an electron because it's a nonmetal and they gain electrons. So the ionic chlorine is called chloride, okay? So to put these together, we need 2 chlorides for every cobalt. So that's the formula. Second of all, do we know the physical state? Yes, because we know from the solubility table, which is right below the activity series, that the chlorides are soluble unless they're bonded or partnered with the heavy metals, silver, mercury, and lead. Well, cobalt's not one of them. So this is soluble. Okay. Cobalt is solid and aqueous, HCl. So we have the equation. Okay. Now let's balance. Well, I got 2 chlorides to the right. That means I got to put 2 in front of HCl. Okay. That boosters up my hydrogens, which is okay because I already have 2 hydrogens in the form of hydrogen gas. I got 1 cobalt, I have a balanced chemical equation, okay, with their states. So Let me clear this out and bring in the reaction. Okay. So we were given this information, just simple information, HCl and solid cobalt. We had to figure out what kind of product do we have. Well, I don't know which reaction. So what did I do? I went through a process of elimination of the reaction types that are out there. Okay. And ended up that there had to be a single replacement reaction. Well, that would mean that the cobalt is replacing the hydrogen, right? The single replacement reaction. Normally, you see two metals here. One's an ionic form, one's an element normally. But always remember that that activity series is relative to hydrogen and H2. And relative in the ionic form of hydrogen is H+. Okay. All right. That being said, now we can do some calculations. And they're giving us some information here. It says, how many liters at STP? That's a key point. STP. What does that tell you? Well, that means I can use this relationship. 22.4 liters per mole. Okay. Full form if 5 grams of cobalt reacts. So we have 5 grams of cobalt. And they want to know how many liters of gas. Well, we only have one gas, and that's this guy. It's got to be hydrogen, right? So our relationship is simply between the cobalt and the hydrogen gas. And we want to know how many liters that would produce. Okay, so let's put down what we're given, 5 grams of cobalt. Okay, well, we need, what is it? Wait, yeah, look that one up. Cobalt, where are you? 58.93. 58.93 grams per 1 mole. Okay. First step, we're going to convert 2 moles. Okay. What we're given, we can't do anything without converting into moles. That is a common factor. And so I need it's cobalt, so I just simply look up the atomic weight. Second factor, that gives me the moles of cobalt. Grams of cobalt, and my units cancel here, so I'm good. So now I got to get 2 moles of hydrogen gas. And I go through the equation, the balanced chemical equation, that is simply 1 H2 and 1 cobalt in that reaction. It's a 1-to-1 relationship. So that means now that my cobalts cancel, leaving me with moles of hydrogen. And since I'm at STP and I'm looking for liters, guess what? I can use that relationship of 22.4 liters per 1 mole for any gas. My moles cancel. H2, liters of H2. And now, unit-wise, I'm left with liters of H2. Okay, so I got that set up properly. Let me clear that up and bring in the clear one. Okay, here we go. 5 grams of cobalt, which is what I'm given. I got to convert that to moles of cobalt from the balanced chemical equation. Keep in mind, I'm following that flow chart. Okay. All right. I got this one converts me to moles of hydrogen gas. I'm at STP. Now that converts me to volume hydrogen gas. So therefore, under these conditions, 5 grams of cobalt and sufficient hydrochloric acid will generate almost 2 liters of hydrogen gas, 1.90. Okay. And so if you look at that flow chart, guess what? Whoa. What direction we were at? We were at we were right here and we went down here, right? Nope, we're right here. Sorry, let me change this color here. We were grams given and we went looking for moles. Okay, so we went diagonally. Okay. Now the question asked is, if 2.374 liters of hydrogen gas formed, how many grams of HCl react? Okay. And so again, keeping track of what two components we're working with, and that is HCl and the H2 gas, right? And so if 2.374 liters of H2 or hydrogen gas was formed, right? How many grams of hydrochloric acid reacted is the question. And so again, as always, we write down what we're given and got 2.374 liters of hydrogen gas. That was how much was formed. We need to convert that to moles, okay? We're at STP, so we can utilize this relationship. If STP was not there, it may say 0 degrees in 1 atmosphere. That's STP, and then you can use that. If it says any other temperature, then you can't go any further. You say not enough information. Cannot calculate. Balanced chemical equation, it's a 2-to-1 ratio. And this puts us into the moles of hydrochloric acid. Now that we're at the moles of hydrochloric acid, I need the molar mass of hydrochloric acid, HCl, to give me the grams of HCl. Okay. And so you can see that liters cancel, moles of HCl cancel, leaving us with grams of hydrochloric acid. Okay. 7.2. All right. Let me you know what? I got 335. Let me just stop it here. There's slide 13. Chapter 13, page slide 8. Okay, we'll stop it here. The next one, like I said, we'll knock this out. I might give you a few more examples and then we'll move on to 14 and we'll be done with that. All right, so